Okay, last time we have seen some constructs, some language elements. Now today we will start with the concurrent constructs. Now I've already spoken about concurrency and the characteristic of VHDL as far as concurrency is concerned. So we'll go into a little bit more details. So what are the various different types of concurrent constructs? Now these constructs are very essential when you actually start writing the VHDL design. Okay, we'll see a couple of examples also. So there are two concurrent constructs. Please remember, when I say concurrent, it means that they are as if these constructs are in terms of the conventional programming languages simultaneously. Okay, so when I put so many when, else or with select kind of constructs, it is rather understood that these will work in parallel, that is simultaneously or concurrently is a simple plain words. So when else and with select are the two constructs. Let us go into the details of when else. So it is a concurrent statement which assigns one of the several expressions to a signal depending on the values of Boolean conditions which are tested in sequence. Now this is a very peculiar kind of construct again. So don't get confused between when else and with select. These are very important constructs as far as the different types of devices that you want to design are concerned, like the multiplexers, etc. Okay, so this concurrent statement will assign one of the several expressions to the signal. We already have seen what is a signal, right? So it is equivalent to a process containing an if statement. So this is some sort of a alternative to a process containing an if statement. I know we have not done process as yet, but just keep this in mind. This is the syntax. So you have an optional label, then you have the target. That is what exactly do you want to assign. Okay, then you have a lot of options. Expression. These options are also, I mean, they are optional, so you need not really do that or write anything over there. Expression. After some whatever, I mean, this after is also optional. Whatever is written in the square bracket is optional. Okay, so if you want to assign something after a particular time duration, that also can be done. Okay, when the condition. So this condition is important. Expression when condition. You just look at it. Target is assigned some value when expression. What is that expression? When condition. When that particular condition is satisfied. This is will be clear when we actually see one example. Okay, so just have a look at the syntax. So where do we use it, or where is it possible for us? Where are the valid uses? So in architecture, after begin and before end, we are going to see what is a block later on. Just remember that you can put it inside after the begin and before the end. We are also going to see generate after begin before end. So these are the possible places where you can use this particular construct. There are some rules which you have to use, which you have to follow. The reserved word guarded may only appear in a signal state assignment within a guarded block. We are going to see guarded blocks. Of course, it's not there in the syllabus, which is for sake of completeness. We are going to see that also. A guarded assignment only executes when the guard expression on the surrounding block is true. We will see that with an example. Don't worry about that. An expression on the right hand side may be replaced by the reserved word unaffected. Now this is important. Very, very important. When you don't want anything to happen, if the default conditions are not met, in fact, the default condition happens to be unaffected. So you don't want anything to be assigned to the signal. Simply you have to put unaffected. What does this synthesize to? So conditional signal statements are synthesized to combinational logic. Very, very important. So remember that these kinds of statements, conditional signal statements for this particular construct, are synthesized to combinational logic. So it will generate a combinational logic. So you have to correlate these things when you have started coding. You will see that these kinds of rules are to be followed, and then once you follow the rules, the synthesis happens, or synthesis is carried out, and then by the synthesizer, and then you can get the construct. You can get the actual logic. Expression on the right hand side are multiplexed. So this is actually a very good start point when if you want to start designing a multiplexer. So this kind of construct gives rise to a multiplexer kind of a logic. Resulting logic will be priority encoded. This is one very important difference. Remember, I already said that here, which are tested in sequence. Once we have this kind of condition that they are tested in sequence, it means that it is going to impart what is called as a priority. So a very simple, it's a very important construct from the saying that if you want to have some kind of priority encoding or priority encoder, if you want to design, you have to use this construct. Okay, that is it. Conditional and selected signal assignments are concise way to describe combination logic in RTL descriptions. Although some processes can be easier to read and maintain in some cases. So as I said, this is an equivalent to process which is containing the if and all those kinds of things, the sequential statements which we are going to see later on. So this is a different way of doing the same thing. Conditional assignment is a neat way to convert from a Boolean condition to a type STD logic. This is also important because if we are having only a Boolean expression, in that which is happens to be a signal is 1. Else B when S2 is 1, else C. Okay, so the default is C. All right. And what does this manifest into? Okay. How does it synthesize? How does it get synthesized? What is inferred? That is the best word. What is inferred by the synthesizer if we write something like this? It is like this. Okay. So if you want to have a logic in some this possible way, then this is a very, very good thing. Okay. In fact, what you are getting here is some kind of priority also. Okay. A very useful, let us say, component is a tri-state buffer or a high impedance buffer. Okay. What is a high impedance buffer? What is a high impedance buffer? Yes. Can you tell me what is a high impedance buffer? Guys? Hello? Please respond. Guys? Are you there? Snehal? Karishma? Guys, why don't you respond? Hello? Are you not there? Guys, please respond. Respond, please. Why don't you respond? It seems you're not there at all. Snehal? What's wrong?
Hello, sir.
Hello. Why aren't you responding?
Hello, sir.
Yes, my question is, why aren't you responding at all? I've been speaking for quite a lot of time and nobody is responding. Then I came to know that you are not there online.
सर मी खूप वेळ झालं बोलतेय पण माझा आवाजच जात नाहीये तुम्हाला.
And what about this second girl, Karishma?
Sir, there was some network issue, but now it's okay.
Okay. All right. Now, is it okay? The network and all that?
Yes, sir.
Yes, sir.
Yes.
So I was talking about a high impedance buffer. What do you mean by high impedance buffer? That was my question. Or it is popularly called as tri-state buffer. How does it work? What is it expected to do? Do you know that? Yes or no?
Yes.
Then
So
tell me.
buffer in the sense it's like there's some distortion in signal. Buffer means that, but what high impedance buffer, I exactly don't know what it is.
Okay, so buffer is just, we know that it is a buffer, but it has got one additional feature, and that is its output can be put into high impedance state. Okay, so look at this example architecture. I've written the name as try_buff, that is buffer of try_buff_part is. So all this syntax has to be carefully understood. Begin and else. You can see the very first thing over there as begin. After begin, you can write there out.
Out less than equal to.
Yes. So what we have here is less than or equal to. It's not less than or equal to. It is assignment. Last to last lecture, I have already spoken about the assignment.
Yes, sir. Assignment operator, right?
Okay. So out one is assigned in one conditionally when some input signal, that is a control, is equal to 1. Otherwise, the out one by default is high impedance. This is how the tri-state buffer will be written. Look at how it gets implemented. So it is this thing that is going to get implemented, the control signal. I'm getting some noise from somebody. All right, so this is what you will the synthesizer will infer that you want to implement such a kind of high impedance buffer. Now this is a very important thing when you want to, again, when you are sharing the common bus. Okay, when you are sharing the common bus and you want in one sometimes to be active, some other input into maybe with some other buffer is going to be sharing the same line. In that case, I can put the control, using the control, I can put this into high impedance state, and then I can use the next input to activate the, to put the values on the line. So that is basically a tri-state buffer. Have you understood the function of tri-state buffer and how it is written?
Yes.
Yes, sir.
Okay. Next is the with select. Okay. It is again a concurrent statement which assigns one of several expressions to a signal depending on the value of the expression at the top. Okay. And this is equivalent to a case statement or a switch statement in C language. Okay. Very similar to that. This is the syntax. Again, with expression select. Target is assigned expression when choice 1, expression when choice 2, expression when others. So this is a typical syntax for with select kind of choices. So this is a very important thing. You should not have multiple expressions leading to the same choice. Okay. Expression on the right hand side may be replaced by the keyword unaffected if you don't want that to happen, anything to happen. All possible choices must be enumerated. This is very, very important, and that is the reason why we have the others clause. Okay, so maybe possible that you are not enumerating, or maybe you are not exploring all the possible combinations of the input. And if such is the case, you don't want anything to happen in such left out one combinations, you can simply use the others clause. You can see with an example. First, synthesis. Selected signal assignments are synthesized to combinational logic. As again, expressions on the right hand side are multiplexed onto the target signal. Okay, let us see with an example. Remarks first, conditional and selected signal assignments are a good way to describe combinational logic. So this again gives rise to combinational logic in RTL descriptions. Example is a multiplexer. Now this is a standard example. Here we don't have anything like priority encoding. So that was covered in the last construct. So architecture, multiplexer 4 to 1, that is for 4-1 of multiplexer is begin. So we are assuming that we are already written the entity and it has got A, B, C, D and Z as the std underscore logic types. Okay. So with control, so the control signal is what is going to be the driving factor here. With control select Z, which is output, which is assigned A when the combination, that is control, is actually a 2-bit, it's a vector. Okay, so 0 0, B when 0 1, C when 1 0, D when 1 1. Okay, and to cover all the other cases, we have to write Z, that high impedance, when others. Now, is there any possible condition then? Anything is left out? If it is a 2-bit vector, anything left out? 0 0 0 1 1 0 1 1, all possible combinations?
No, sir. Yes, sir.
Then why do we require still when others? There is a certain reason why we are having this. Because if you have understood correctly, std underscore logic is a multi-valued logic. So combinations are not only restricted to 0 0 0 1 1 0 and 1 1. There can be other types of combinations also, isn't it? Do you remember the multi-valued logic?
Yes, sir. Like
one can be high impedance, the one input can be high impedance, one can be uninitialized, and all such combinations. So in such situations, what should happen? We just want that the output should go into high impedance when other such combinations occur. So we are not leaving out any combinations, and the keyword that makes it happen is when others. So please remember, always whenever you are input, that is your control, is of a STD logic type, in that case you have to make use of when others, otherwise you'll land up with some wrong results. Agreed that if it is a bit type, then no issues. Again, of course, bit type has got 0, 1 and high impedance. All right. So again, when others, you will have to use there also. But then remember that whenever you are using STD_logic, other combinations, other values are possible, and that you have to, let us say, cover in your construct. So this gives rise to a simple multiplexer like this. I hope you know what is a multiplexer and all. Okay?
Yes, sir.
Is this fine?
Yes, sir.
Okay. Next is construct called as a block. There are two types of blocks. We have one, a simple block, and the other one is a guarded block. Okay, simple block in its simple form represents only a way of locally partitioning the code. Okay, let's see with an example. It allows a set of concurrent statements to be brought together or clustered into a block with the purpose of turning the overall code more readable and more manageable, which might be helpful when dealing with long codes. So block is a neat way of simply restructuring or partitioning the code. Okay, it will consist of all concurrent statements. Please remember that. So this is the syntax. We have the optional label, then the block, keyword. You can have some declarations, begin, write down all concurrent statements, and end block. Okay, so block is one very important way of making the code a little bit more manageable, specifically when you run into long codes. Okay, general form of architecture using block for partitioning is like this. Architecture, begin, you write down one block, do something here, again do something here. So but all these are concurrent, please remember that. Okay, so you can simply partition the code. Block can be nested inside another block. So you can have block, again you can see here that there is a nested block here, and all the concurrent statements are there. Also be done. Then there is something called as a guarded block. Guarded block is a special kind of block which includes an additional expression called as the guard expression. Guarded statement in the guarded block is executed only when the guard expression is true. So this is a conditional execution. So you have the block and you have the guard expression that tells this that this is a guarded block. Again, similar to the block, again you have begin and then lot of concurrent statements which are guarded and unguarded both, and end block. Even though only concurrent statements can be written within a block, with a guarded block, even sequential statement circuits can be constructed. Please remember that it doesn't mean that only concurrent statements or the concurrent constructs can be used to construct the combinational and sequential. For sequential statements useful only for sequential, it is not like that. Okay, so it is quite possible that you can generate combinational logic with sequential statements also, and vice versa. Okay, here we are talking about a latch. Okay, so library IEEE, the complete example is given here. Use IEEE STD logic 1164.all. Entity latch is port. I'm having the port declaration as B. Clock, which are in mode, and STD_logic type. Q is output, and it is of STD_logic type, end latch. Architecture latch of latch, I mean the name of the architecture and entity can be same, is, you see here, begin. B1 is a label block. Now this is a guarded block. This becomes a guarded block. So this will execute only when clock is equal to 1. Okay, so it says begin. Q is a simply assigned guarded D, and end block. That's all. So this is this, with the help of this structure you can create a latch. You can create flip-flop also. Here it is shown as a D flip-flop. Port declaration is all like this. Then architecture. Now here the expression, guard expression is clock tick event. All this clock tick event and all those things later on. So this is one particular condition. Clock tick event means there is a rising or the falling edge of the clock when the clock level changes. And clock equal to 1 means it is a positive edge which we are going to trap. So the event that clock is changing, and at the same time if clock is going 1, simply means that this is a rising edge. Please remember this. We are going to use this quite often. Okay. Then Q is assigned guarded 0 when RST is 1 else D. So with such a kind of thing you can create your own D flip-flop. Remember that. So D flip-flop can be again inferred in multiple ways, where this is one of the ways. So what we have here is a positive edge sensitive or positive edge triggered D type flip-flop with synchronous reset. We are going to see what this is, synchronous reset is. What do you mean by synchronous and asynchronous? What do you mean by synchronous reset?
So synchronous means in line, like properly arranged.
When I talk about synchronous reset in a D flip-flop, what does it mean?
Okay.
It simply means that whenever, even if the reset signal appears anytime, the output of the clock will be reset, output of the flip-flop will be reset only at the arrival of the clock. Whereas asynchronous simply means that at any point of time, if the reset pin is asserted, then the flip-flop will reset. It will not wait for the clock event. Is that clear? Synchronous and asynchronous? Is it clear?
Yes, sir.
Okay. So you can carry out some homework problem.
Hello.
This will be your practice problems. And you'll be having
8-bit. So in this, what we have to do in generic encoder, like
you have to implement using DHDL, using the construct that we have seen today itself, right? So the best possible choice would be to use the first type of when else kind of construct, because it is a generic encoder. Or maybe you can use anyone, doesn't matter. We are not saying anything about priority here. So it is a generic encoder. Generic means, okay, if you're not comfortable with generic, try to have something like 8:1 kind of, 8:3 kind of encoder. Okay, but at least start with this practice problem. And then the 8-bit ALU. So I'm going to give you the operations using simple logic, simple constructs that we have seen so far. You can write down this. Of course, I'm not expecting this to be done immediately, as and when we cover so many things. This is part of your assignment, will be your part of your assignment. All right. Just keep it in mind. Copy this down, get a snapshot or whatever you would like to have. Okay? Is that okay?
Yes, sir.
All right. So yeah, this is the third assignment, priority encoder. Now here you'll have to use the first construct. Okay. See what is copied on the problem statement. The circuit must encode the address of the input bit of highest order that is active. So 000 should indicate that there is no request at the input. There is no bit active. You can see here. So this is having the priority. So even though input number 2 and 3 are still asserted, the highest input is going to be displayed over here. So this is what is expected. One 110 is what? Binary?
Sir, 4 to 6.
Yes. So it simply means that the input number 6 is active. If this was 0 and this was 1, it should have given me all ones. Have you understood the concept of priority encoder? You must have already done this, but let's say you require some kind of okay. Have you understood this? What exactly you are supposed to do? Okay. Guys, respond so that I can go ahead.
Yes, sir.
All right. Okay, these are the expected waveforms for problem theory. We'll see this later on. Don't worry about that. Okay, so we move on to the next part, that is the component instantiation, which is a very, very important topic. Because this is going to make it possible for you to implement complex circuits. So this is the sorry. Just hold on for some time. All right, is the slide visible now?
Yes, sir.
Yes, sir.
Okay. So we'll start with component instantiation. What exactly do we mean by component instantiation? What is a component? We have to start with that. Component is analogous to a chip socket. It gives an indirect way to use one hierarchical block within another. Okay, so as if you are having a lot of components with you and you are simply connecting those components together. So component is instantiated within an architecture and is associated with a lower level entity and architecture during elaboration using information from a configuration. So component itself is a top level entity, which is of course lower level in this case because you are calling that component in some higher level entity. Okay, so a component is nothing but a simple design that you have written. For example, if you want to implement AND gate, so you write an AND gate and make a component out of it and then call this component in some other design. Okay, so that is a component, and its declaration is similar in form to an entity declaration in that it includes the required ports and parameters of the components. Here the difference is that it refers to the design described in a separate VHDL file. So you are writing the component somewhere else and then you are calling it up. Ports and parameters in the component declaration must be a subset of those in the component file, but they must have the same names. So that is how it is referred to. This will be clear when we actually see an example. So component can be declared in main code itself, or it can be declared in the library also. Okay, this is one important thing that you should remember. So I can declare the component in the main code also. Component can also be declared in a package. All right, and then in the main code you can call it up. So this is the syntax for component declaration. So component name, generic. We are yet to see what is the generic, but this is just kind of, let us say, the default values. For example, if I want to have model 7800 IC, in that case, 7800 is what? NAND. It's a TTL NAND gate. So it will be having some parameters like the propagation delay or high to low T, HL, TLH. Okay, propagation delay is like that. So if I want to model that exactly, I can use these generics over there. We are going to see in more details about these generics. Then the port. So the port input name, just like the entity, we can declare the port here. Okay. Exactly like an entity. And then end component. And where can I declare the component? Inside a package or after architecture is before begin in architecture, before begin in block, and before begin in generate also. Okay. So this is how you will declare the component. What are the rules? For default configuration, the computer is as a black box. Please remember this. Okay. So in version of VHDL, which was revised in 93, components are not necessary. It is possible instead to directly instantiate an entity within an architecture. So that they have made the changes. This is an example component which I am declaring as a counter. Generic is just n, which is an integer, which is some sort of a constant. Assume it to be constant for the time being. Then I am declaring the port as clock reset enable all in type, in mode, std logic type, q as a buffer type, okay, buffer mode, sorry, std logic type, logic vector type, n minus 1 down to 0. Now with this kind of thing, it becomes a generic counter. Okay, n minus 1 down to 0 means it's a generic counter. So if I want to have declare something generic and then assign the value of n later on somewhere, in that case I can do it. Okay. Instantiation, the concurrent statement is used to define the design hierarchy by making a copy of the lower level entity within an architecture. So what is instantiation? It is simply making a copy of the lower level design. Of course, by on its own, it is itself a concurrent statement. Direct instantiation of an entire of an entity bypasses the component and the configuration both. So you can directly now, after revision, you can now use a direct instantiation also. So this is the syntax. So you have instance label, component name, entity, configuration. This will be more clear with an example. Okay. So where can you use it? In architecture, after begin, before end. In the block, after begin, before end. In generate, before, after begin, before end. What are the rules? An entity architecture or configuration must be compiled into a library before the corresponding instance can be compiled. A very, very important thing. First of all, you have to compile this architecture, entity architecture or configuration before you are compiling it, before you are using it for instantiation. However, an instance of a component can be compiled before the corresponding design entity has even been written. So that is, instance can be compiled, no problem with that. So example is, let us say G1, which is the label, NAND 2. So saying that this is a 2 input NAND gate. Now generic map happens to be 1.2 nanoseconds. So this is a time. This is nothing but the, let us say, your propagation delay. Okay. Then you have the port map N1, N2, N3. Obviously N1 and N2 are inputs, N3 is the output. And then you have some other entity, which is other component, which is called up, which actually happens to be in the work directory, the package, and named as counter. Okay. So The port map for that is clock reset count. So in this way, basically you can call that entity and then you can use it. We'll see with an example. So what is a generic map? Time is ripe for understanding what is generic. It is used to define the values of the generics, usually given in an instance, but may also appear in configuration. So generic map. So what we have here is a generic map. So generic map means all these values are attributed or given or assigned to those particular generics which are there in the entity itself, which you are instantiating, which you are calling up. Okay, so the mapping has to be, there are two possible ways in which you can map it. One is called as a formal and the other is called as actual. Okay, we'll see with an example. So where can you use these generic maps? Here, label component name and before the port map for use. Let us not talk about this because we have not yet done this construct as well. Just remember this. What are the rules? The two forms of syntax, order list or explicitly named choices, can be mixed, but the order list must come before the name choices. Now there are, as I said, there are two ways in which you can have this mapping. So instead of, you can have mixed mode also, but then I recommend that you use only one time. Remember that the generic map does not end with a semicolon. So we'll see with an example. The example here states architecture structure of entity is component. Now I'm declaring a component here as NAND2 and the generics of the component. So these are the generics belonging to the component TPLH and TPHL belonging to the type time, which is 0 nanoseconds, for example. It can be anything depending on the model which you are trying to use. Then port map A, B are in type, F is out, both are STD logic and component. Now if I want to call this component, what I will do? I will simply declare it as with a label. These labels are important here. They are not optional, remember that. So G1 is one component which I want to instantiate. What is the name of that component? NAND2. This should match. Okay. Then the generic map. So if I provide this kind of generic map, it simply means that TPLH is 1.9 nanoseconds, whereas TPHL is 2.8 nanoseconds. This is an ordered list. And then the port map, the names are different. I'm calling here it as N1, N2, N3. It simply maps to N1 is A, N2 is B, and N3 is F. Okay. Another way of having the generic map is G2, NAND2. So again, this is the second component which I'm instantiating. And generic map, now this is the formal, let us say, mapping. TPLH, exactly the names are to be used here. TPLH is 2 nanoseconds, TPHL is 3 nanoseconds. Now, if you don't remember this order, then this won't work properly. I mean, you may run a bit trouble. This is the more preferred way because it explicitly tells you that what type of generic is to be used where. Okay? So this is how you can instantiate a component. Is this clear to all of you? Guys? Guys? Yes, Nehal, have you understood?
Yes,
Have
sir.
you understood? Karishma,
Yes, sir.
have you understood?
Yes, sir.
Are there any
Right.
doubts? As far as component instantiation is concerned, are there any doubts?
Sir, I wanted to ask, the lecture is being recorded, so where can we get this recording?
Yeah, I'm going to put it on the YouTube.
YouTube, sir. How? So what should we search?
That is my responsibility. I will let it be known to you. Okay?
Okay, sir.
Okay. All right. So do you have any doubt with this?
No doubt.
No doubts. Okay. So a port map is typically used just like the generic map. We have the port map. It is used to define the interconnection between instances in a structural description. Port maps signal in an architecture to port on an instance within that architecture. We'll see with an example, so things will be clear. So what is the syntax for port map? Again, we have two ways in which you can do it, formal and actual. What are the rules? The two forms of syntax, order list or explicitly named ports, can be mixed, but the order list must come before the named ports. Within an instance, the formals are ports on the component or entity being instanced. Actuals are signal visible in the architecture containing the instance. This will be more easily understood by you when we go for an example. With a configuration, formals are ports on the entity, actuals are the ports on the component. If actual is conversion function, this is called implicitly as values are passed in. So all this means how you are supposed to use these port maps. The example will make it more clear. Component, we have a component called as counter, which we have declared somewhere, maybe in the entity or maybe in the package. And what are the various ports? Clock, reset or in type, in mode, standard logic type, up, down, in mode, STD logic type, which by default is given a value of 0, okay, or low. Q is the out. I'm using the counter 2 times. Okay, one is called as G1, and the port mapping is like this. So you can have an ordered mapping like this. So this clock 32 megahertz will mean clock, RST means reset, open means up down, and count means Q. Okay, so this is an ordered list. Okay, named association, order doesn't matter here, so you can write it any way you want. Reset is RST, clock is clock 32 megahertz, Q3, that is the MSB of the output, is they are calling it as Q2 megahertz. Q2 is open, unconnected. Q1 down to 2, it's a 2-bit vector, which is the subset of the output, which I am calling as CNT2. Okay, and up down I am assigning to open. So both the ways in which you can assign these port maps. So as you can see, I'm having a top level entity like this, and inside that I'm going to call this lower level entity 2 times. Okay, so it will look like this. Just have a look at it. Understand all the signals properly. Fine. Just try to correlate it with whatever we have seen here. Now, why I'm stressing on this is because component instantiation is a very important part of VHDL. So, in fact, I want all of you to write this down and then compare it with this figure. Please do that. Write this down and tell me when you are finished. You need not write component counter, of course, it's necessary. So, do that, no problem. Write everything down, and then we are going to compare it with the figure which I have shown you already. Do it, please. And once you are finished, you tell me. Please write this down. This will ensure that you are actively participating in the lecture.
Okay, sir. So this one, na example component counter and all.
Yes, write it down.
Yes, sir.
Tell me when you are finished.
Done, sir.
Finished?
Yes, sir.
Sheikh Ahmed, have you joined for the first time?
No, sir. But I have joined the late, so it is from the last week I have joined.
Okay, okay. ठीक है.
But I have attended 2 to 3 lectures.
All right, all right. Okay, so if you are finished copying this down, all of you are finished? Have all of you finished? Guys? Okay, I assume that you have finished it. Moving on to this picture. Try to correlate each and every signal and the port. Starting from the ports of the top level entity and mapping it to the two low level entities which are called inside using component instantiation, and see what you come out of it, how it is mapped. Are you able to correlate the maps, port maps? Guys, respond please. Guys, are you there? Karishma?
Sir, what is Q2 megahertz?
Come again?
Q2 megahertz.
It's just the name. It is just the name of that pin
Okay.
of the high level, the top level entity. You see here, this one.
Okay. So we are just naming it.
Yes. Mac.
Okay.
This is 2 megahertz. This is a 4-bit counter, see? So how many states are there? 16.
16.
Right?
Yes, sir.
And when will this bit, when will it be high? When will this bit change?
Okay. Up, down, up. Another.
When will Q3 be high? After how many clock cycles?
8.
6.
Sir, after 8 clocks,
Yes.
in the 9th clock.
Yes.
Sir, how?
No, you're not able to understand this.
No, sir. How after 8
See what is happening? This is a counter. And this counter is driven with a 32 megahertz signal, a clock. Okay?
Yes. Yes, sir.
So when will Q1 change or assert at what rate? Q0. When will this change? Have you understood this? When will Q0 change? You are dividing this clock. It's the division of the clock, no? At various different levels, you divide the clock. So this will be divided by 2, this will be divided by 4, this will be divided by 8, and this will be divided by 16.
16.
You are getting it?
Yes, sir.
And divide by 16, 32 divided by 16 is how much?
2.
So that is why we are naming it as Q2 megahertz. Anyway, the function is not important at this point. What we want to do is, we want to make sure that you are calling two components and you are making use of those two components to create a bigger component, a bigger entity, to be more precise. Are you getting this?
Yes, sir.
And that is the reason why I'm calling this as 2 megahertz. It really doesn't matter. What I want to do with it is later on. How it is done is this way. All right. You can see that reset is common to both. Up down, we are not interested in up down because up down we are already making it 0. So it is always going to be as a up counter. Okay, so there is no need of providing any external input to up down here. We are always making sure that it is counting up. Okay.
Okay, sir.
So that is how you can use already compiled components and then design your own entity, top level entity. So this is just, we'll have to look at a simpler example so that now things will get concretized, your ideas will be get concretized. So let us say I want a 4 input some kind of component called as ND4. Okay, and the ports are in 1, in 2. So this is the 4 input device and Z is the output. Z is not high impedance here. Z is the name of the port. Okay, architecture of this entity ND4 can be written. Now I'll be using 2 input gates, for example, or 2 input components to create this entity. As you can see here, I'm declaring component as ND2. All right, it has got A, B as input, C as output, end component. So the component declaration part is over. I'm declaring some intermediate signals which correspond to wires, as I said, connecting wires as temp1 and temp2 belonging to STD logic. And here you start with the actual architecture. You are calling one component, labeling it as U1, mapping the port of the main entity like this. So A is mapped to in1, B is mapped to in2, C is mapped to temp1. That is the output. Okay, output is mapped to temp1. For 2, in3, in4, output is mapped to temp2. And then combining these two to form the output Z. Okay, so it will be like this. Just go through this. Again, try to correlate how we have done it. You see U1, U2 and U3 are the same components. I'm calling them these components. I'm calling this component 3 times to construct a bigger circuit. The only thing that is required for me is to map it properly. Wire it up. In simple plain words, wire it up. So these signals actually work just like wires for connecting the output of this to output of this. Is this example clear? Yes? Guys?
Sir, can I see the code once?
Sure.
Sir, where are we landing it? Means we have not written any code regards to NAND. We are using NAND gate.
That is what I'm saying. That component is already pre-compiled.
Acha.
That was what I started off right in the beginning. You getting it?
Yes, sir.
This is already a pre-compiled device, a component, which you are calling, declaring that component and calling it.
Okay, sir.
Okay. Clear to all of you?
Yes, sir.
All right. So we move ahead. So now we come to one very interesting statement called as the generate statement. Okay. Concurrent. It's a concurrent statement used to create regular structures or conditional structures during elaboration. So this is a shortcut for generating repetitive or regular structures. It is used to create multiple copies of components or processes or blocks. Again, it provides a compact description of regular structures such as memories, registers, and counters. Okay, we'll see with an example. Two flavors of generate statements are: for generate, number of copies is determined by a discrete range, and the second one is if generate. So 0 or 1 copy is made conditionally. So there is a fixed number of copies that you can generate with for generate, and if generate, we can have it conditionally. But the range must be a computable integer in any of the following forms: integer expression to integer expression down to integer expression. Each integer expression evaluates to an integer. Please remember that you cannot have a real number over there or a decimal fraction over there like that. Obviously, why we are restricted to integer only? Let me ask you this. Why is it restricted to integer only? Simple common sense. Yes? Guys, answer me.
Sir, because it's hold ranges.
Guys,
Yes, sir.
can you ever have 3.5 NAND gates? Yes or no?
Sir, what? Three and a half?
Yeah, 3.5 NAND gates. Have you seen something like that?
No, sir.
No, sir.
It is not possible. And that is the reason we must have integer. Okay, it is determined by number of copies. It's going to be hardware. Please remember, we are thinking from the point of view of hardware. So you cannot have 3.5 registers, 4.25 counters. They'll be always integers. 10 counters, 4 counters, 5 NAND gates, 6 NAND gates, whatever. Okay? So it has to be an integer, computable integer. This is a syntax. So instead of this cryptic syntax, let us see where exactly how it is used. Where architecture after begin, before end, after begin, before end, after begin, before end for generate. Okay. So in generate, you can use still more generates. Remember that. The rules are range and condition must both be static. What do you mean by static?
Fixed.
Yes.
So, fixed position.
It is not going to change during the lifetime. Some sort of
Yes, sir.
constant. Okay. They cannot include signals because signals are changing. Label at the beginning of the generate statement cannot be omitted. This is one very important thing. Otherwise, we have already seen that labels were optional, but not here. Again, synthesis is straightforward, right? So this is again synthesizable. Please don't forget to update your notebook, last page of your notebook into 2 columns, synthesizable and non-synthesizable. So this is an example. Architecture ABC of full adder is, I am declaring a component called as full adder with PA, PB, PC as in, PC out as PSUM as out, signal as STD logic vector. It's a 5-bit vector, remember that. Begin C0, okay, is assigned C in, that is a carry in from the previous, let us say previous circuit. GK is the label of that generate statement for K in 3 down to 0 generate. Please look at this very carefully. You copy this down because later on you will be required to map it properly to hardware. So the upper or the outer loop for k in 320 generate, and this is the inside that loop we have, again we are instantiating this full adder which we have declared earlier and mapping the port like this. So what do you think will be inferred? Just give it a thought.
Sir, it will be generating multiple full adders.
Just 1 second, please. All right. So yeah, what were you saying?
Sir, it will be generating multiple means four full adder.
My recommendation is that you try to figure out what it will generate on a piece of paper right now, and then I will display the answer and see whether you have got it correct or not. This exercise is for all of you. Once you have finished drawing, just let me tell. Just tell me so that I can show you the answer. Yes, have you finished? Guys?
No, sir, doing.
Okay, continue.
Done, sir.
Okay, so just verify whether you're getting the same thing.
Yes, sir. Almost.
Almost.
Yeah. Yes, sir. Means I was a little bit confused with C out. I have named C out 1, C out 2, C out 3.
That's fine. That's fine. But do you get the idea of what generate can do?
Yes, sir.
Sir, can you show the question once? C4. Okay, sir. Okay.
All right. Okay. Guys. All right. So we proceed with another example. Architecture shifter of shifter is now here the basic component to be replicated is D flip-flop. We already know that D is the input, clock input, Q is the output. Okay, one more thing of concern is that for K in 3 down to 0, how many full adders were generated?
4.
That's it. So you just have to remember this.
4.
All right. So here D flip-flop is the basic component, and I'm generating using generate statements for K in 0 to 3. Now I'm using it in a different way. Generate, and now you are having two more generates as a matter of fact, conditional ones. So if K is equal to 0, generate a D flip-flop. Okay. This is the label. D flip-flop is the label. DFF is the component which you want to instantiate. Port map clock, count clock, and QK, and end generate. Then another generate, which is again a conditional one. If K is greater than 0, you have another construct. Now try to figure out what this does. Remember, it is going to generate flip-flops. Okay? Work this out as well. Finished? Yes, have you finished?
Yes, sir.